Yes.
Okay. Do you see a pointer?
Yes.
Okay, then I could not be more happier. Okay. Yeah, so thank you, Rafik, for inviting me to join this exciting lecture series. And I'm very sorry I could only join now, but I had another presentation just before. But still, I'm sure that Rafik told you interesting and exciting stuff, because for that I know him well enough. And I will hope that I can also contribute some interesting aspect of our work in that area. And the topic I want to be discussing about is computer-aided molecular and process design, more than products actually, based on PC-SAFT and quantum chemistry. And since Rafik asked me to introduce myself, I will briefly do so. So I'm André Bardow. I'm a professor here at ETH Zurich in Switzerland, but I used to be since last year in April. And before I was for 10 years a professor in Aachen for technical thermodynamics. And that's maybe the reason why our work tries to employ heavily thermodynamic models in order to exploit the predictive powers that we see in these methods nowadays in order to use them for engineering applications in designs. And in order to jump into the presentation, I want to emphasize something that you've seen and I heard you discussing is that molecules are very central to what we are doing as chemical engineers and also in energy technologies. Thus, if you look at a lot of technologies that we are discussing that are exciting today, is it batteries? Is it the development of sustainable fuels? Yesterday, the largest CO2 air capture plant was opened in Iceland, and also in the energy sector, we are looking at new novel technologies like, for example, organic Rankine cycles. And in all these systems, the choice of a molecule that we're actually using is very often the key to the performance. And very often today, this is handled intuitively, the selection of the molecule, but the tools that Rafik, for example, has been pioneering and developing has been helping us to identify the molecules that are actually the top molecules for an application. And what we try to develop is molecules or products that are actually the best molecules, the top molecules. And I don't know whether the symbol is familiar, but there's a TV show, there's countries looking for the top models. And this started yesterday in Switzerland. So Switzerland, we are looking for Switzerland's next top model. And so in this presentation, I'm kind of looking for a top molecule. And to be quite honest, this is much more difficult than looking for a top model. Why? Because there are much more molecules in this universe than people, at least as far as we know. So I just checked yesterday the CAS registry. And if you just know for the molecules we know already, there are 187 million unique chemicals registered in the CAS registry. And so the task we are facing, if you really want to live up to our expectation, is to say, how do I filter basically out of these 187, if I limit myself to the ones we know already, how do I filter out of these 187 million molecules that top molecule for an application, which one to put into this organic Rankine cycle? Now, being a professor, the solution is easy. Hire a lot of PhD students and let them do the work, but that is even not feasible with PhD students. So the solution has to be in the computer. Yeah? And so what I want to be presenting is not surprising in a PSE for Speed seminar. I want to presenting the methods we have been developing in order to support this task to identify the top molecules. And I said we, so I want to briefly introduce to some of the key players, and I will show some more faces along. I just want to emphasize that the work has not been done by me, but by a lot of smart PhD students have been working a lot of time with me on this, and also collaboration partners. And I'm very thankful for them and our sponsors. And with them, yeah, we faced this problem and we said, okay, let's find the top molecule. And as engineer, the first task, and I have to say that's a very important task in my understanding, is to say what's the metric you measure performance in. And ultimately nowadays, the metric is still economics very often. Yeah, so I'm originally from the European zone, so the euro would be the target. And so we were aiming for. So basically my task then boils down to say, let's look at all the molecules that we are considering for our battery, for our CO2 capture plant, for our power plant, and find the one that makes me the richest, basically, the richest person. Okay, that's a filter what we want. But that's not what many people are doing. If you look into the literature, many people do things they call molecular design, but very often this is based on heuristics. That is a criterion. You look for a molecule that has the right vapor pressure, the right viscosity for an application. Yeah? So this is based on heuristics. Why do I call this heuristics? Because it assumes that you have some understanding about your problem, and you can relate, basically, you know that in order to become rich, your molecule has to have a certain viscosity, but this relationship is far from being non-trivial. So in other means, I only end up with a heuristically optimal molecule, and it might be good, but it might also be bad. I can extend this, I get closer to the target of really finding the top molecule, if I do not only consider the heuristics for physical properties, as I've been showing to you, but we link this molecular selection or design directly to process design. What do I mean by this? So I write down a usually model based on thermodynamics, like the mass and energy balances that all of you have been learning for such a long time. And then I can ask my selection algorithm to evaluate my molecules based on quantities that I can compute from mass and energy balances. My energy demand and energy efficiency, second law efficiency, and so forth. So this brings me closer to the economics, but it's still not the same. Energy efficiency is not everything. In particular, energy efficiency is usually about operating cost, but I don't know how much do I have to pay for my process or plant. And in order to get this information, I have to add equipment design to the equation. So if I know how sizing equations and costing equations, then I have equipment design, and then I can really go down to the economics. And that is compute things like the net present values, like as investment cost and so forth. And if I have a tool that allows me for all these 187 million molecules to design them, to calculate processes with them, and then to design equipment, then I can actually go down to the economics. So the goal of the tools we are trying to develop is that we want to simultaneously optimize these three levels. That is the level of molecular design, of process design, and ultimately equipment design. And the key thing in order to be able to do so is that we need a proper linkage between these elements. And I only joined the end of the discussion just now, but it has been discussed. We need good predictive models. And these models, in our case, have to be modeled for thermodynamic properties. So in particular, if you want to compute heat and mass, heat and energy balances, mass and energy balances, sorry, I need a model for the equilibrium properties of our molecules. And if we want to go to equipment design, that is the size of the plants, then I need to know something about driving forces. And that means I need to know something about the transport properties for all our molecules. And since my ambition was to do all this exercise in the computer, I need a computational model that allows me for arbitrary molecules, at least for as broad design space as possible, to compute equilibrium properties and transport properties models, transport properties. And for this purpose, we rely on, and this is what I initially showed to you, so we rely on modern thermodynamic theories. And one method we've been heavily employing is the so-called PC-SAFT equation of state. So I don't know how intensely there's been covered in this class, in this webinar series. Yeah, but the PC-SAFT model stands for Perturbed Chain Statistical Associating Fluid Theory, so PC-SAFT. It's an equation of state. So what does it mean? It's actually a model for the residual Helmholtz energy given here. And what the model does is basically it computes the residual Helmholtz energy as a summation of different contributions. We have a hard sphere contribution. The model describes chains. That's where the name comes from. So a chain contribution. Then you have dispersive interaction. You have polar interaction. And in fact, by now there are even more terms to take them into account. Now, what is important to us is that this model is really deeply based on physics. So it has a strong theoretical basis. And that also means that the parameters we are using in this model have a clear interpretation and are quantitative, are not like just fudge factors that you are using. So if I want to describe a molecule with PC-SAFT, the parameters I usually at least need is something like the diameter. Then I need the chain length, that's the M, and then I need at least a dispersive interaction given by epsilon. And then I have more parameters, if I like for more effects. But what is important is that we have a set of very few parameters, and these are really physically based because of the theory. And physically based means if, for example, if you plot a homologous series of alcohols and so forth, you will see that these parameters follow smooth trends. Yeah, it's not arbitrary. It's really like the segment, the length of the molecule segment number increases with chain length and so forth. So this already indicates that there's a strong predictive power in the model. And that's a key for us to take this model that has been used heavily in the thermodynamics to correlate data, now also for molecular design. So, and the great advantage of having a model for the Helmholtz energy is, as you might remember from your thermodynamics class, once you have the Helmholtz energy, you take the derivatives, and so you have basically all the equilibrium properties of the system. So if all equilibrium thermodynamics, and that used to be for a very long time, but as I've been pointing out, that's not good enough for us if you want to do molecular design for economic performance. We also need transport properties. And that was a challenge for a long time, but then people have rediscovered, as so often, so-called Rosenfeld's entropy scaling. And that's basically a work from the 70s. And what Rosenfeld proposed is that the transport properties, given here like viscosity, heat conductivity, or self-diffusion coefficients, can be described as a simple function of the residual entropy. And that is a strange result, because at least what I'd like to teach to my students, there's equilibrium thermodynamics and then there's transport properties, and that's really something else. And what Rosenfeld said is, no, you can basically link these two. And the finding is that this really holds well. What you need to introduce a reference value for your property. So these are like ideal gas values for viscosity and so forth. And then we have polynomia in the, as I said, the entropy given by S. So I can write basically this value I know from ideal gas. This value I know if I can compute from my PC-SAFT equation the residual entropy. Then I suddenly can compute viscosity and heat conductivity as shown here over the whole state space. So what are you seeing here? These are experimental and calculated data. You see like the vapor liquid envelope here. And you see like all of the state space, really from the gas phase to the liquid phase, everywhere, the viscosity is computed with this model, and the heat conductivity calculated with this model. And this is a really powerful addition, and I want to highlight that this is available. And again, what we do find is that this is a very systematic approach. That is, we can at least transfer knowledge and develop group contribution methods, for example, in order to predict the transport properties of molecules, which we have not described before. So with this addition, you now can also compute transport properties from a consistent and small parameter set that we have given with PC-SAFT. So I pointed out this goal saying, okay, we wanted to simultaneously optimize molecules, processes, and equipment. Yeah, and what I showed you and to me, and that's maybe one thing I want to emphasize is, yeah, it's really the key to have the right predictive model at hand. And for many applications, the PC-SAFT theory is very, very powerful. And obviously, we can now test models within the model and predict the PC-SAFT parameters, but and predict the performance. But actually, we are optimizing people. So we like to optimize. We want to flip this around, do the design problem. That is, say, please find me the one molecule that gives me the optimal performance. And for this purpose, we can write down an optimization problem. So we do not screen, but we optimize. And this we usually do based on group contribution methods. I'm quite sure Rafik has covered in this webinar really well because he's a master of them. And what we employ is also the group contribution methods. And these are some of the groups we are employing on a regular basis, just shown. So just to recap very briefly, so we do have different molecular groups, and our problem optimization formulation or computational molecular design formulation allows us to connect viable molecules from these group contribution methods, from these groups. Then we have the group contribution methods in order to compute transport and equilibrium properties. And if you feed this into a process model, into sizing and costing models, we can really end up with an economic optimization. And after this introduction, I thought it would be nice for you to look at an example. And the example is not a chemical engineering example, but it's an energy systems example. And one box has been shrinking. And that's a regular power cycle, as you know, like from an average power plant. You're seeing here, like where we put in heat, and we end up with electrical power. So that's what we are used to do. And we used to do it with a lot of coal, but which is not so nice. But we do have other heat sources that are more sustainable. We have waste heat, industrial, or maybe automotive. There might be solar power, geothermal, or biogas. And these heating sources are much more sustainable than those from fossil resources. And so the idea that has been advocated, let's continue using heat-driven power cycles, but let's replace the heat source by something more sustainable. And the nice thing is that you can basically employ the same power cycle, that is your working fluid is compressed, you apply the heat to generate high pressure steam, you expand the steam in a power cycle, and then you condense it again. So that's the same thing as in a big power plant, but usually these heat sources are available at much lower temperatures. So in a usual power plant, we are talking about 600 centigrade. Here we might, with geothermal or solar, we might even just be talking less than 100 centigrade, maybe. And that means that water, which is the usual working fluid in a power plant, is not any more suitable. We need to find another working fluid. Another thing is that these sources are usually much smaller in size, and you also don't want to install a steam turbine, which are by design complex and multi-stage usually, so we have much lower capacities. And in order to accommodate for these two factors, it becomes viable and a good idea to step away from water and to find another molecule that replaces water as a working fluid. And as the title already says, it should be an organic fluid, but there's a lot of organic fluids around. And so what we have been doing, the toolbox I've been describing to you for the simultaneous optimization of molecules, processes, and equipment design, we applied, for example, to this power cycle. Okay, so to show you again, this is the power cycle. I just flipped it around a little bit. So you see here the pump again, then we have the our working fluid at high pressure, we evaporate, we have the turbine and the condenser. And we looked at, and I just show you a case study. So we looked at a waste heat application where we have heat coming in at 120 centigrade, and we can get rid of it at 15 centigrade. There's a couple of design constraints as you would have for a new usual process design, for example, on the pressure. So I can write down, and I think you should be able to write down the mass and energy balances. So we can write down a model for this simple process. And then you need to design also the equipment. A key component here, for example, are the heat exchangers, where we included equations for the sizing and so forth. And these equations you also know, these are these Nusselt relations where you need Reynolds and Prandtl numbers and so forth, which again then means, I need transport properties, which we get from PC-SAFT. So we write down these equations. We write down models also for the design of our turbine. We have different models here in the results I'm going to be showing you. It's a rather simple model, but it has discrete degrees of freedom. That is the number of stages for my turbine, for example. And then we ask, what is the top molecule? And the top molecule in this example for us was to say, we want to minimize the specific investment cost for this power plant, because I'm using waste heat. I'm trying to minimize the investment, the money I put on the table per power that I get out and can later on sell. Okay, so we put all this together. Till now, I spared you mostly equations. And how does the problem look like? Now, it looks like a standard optimization problem. And basically, it's a mixed integer nonlinear programming problem where we do have different equations for the equipment design. We have the transport model for the transport properties. We have model for the process. And then we have the equations that link us the different groups. That's why group contribution is standing here, different groups together to build up molecules. So this is a mixed integer nonlinear programming problem that identifies at the same time the optimal molecule with the right process and the right equipment sizing. What we like to, one reason it's a mixed integer, obviously, it's because we have the functional group sitting in here. So these are discrete choices. And it's nonlinear because we have nonlinear process model equations. What we like to do in our approach is we like first to forget about that it's a mixed integer problem and turn it into only a nonlinear programming problem. Why is that? With this, so if you forget, if you relax the conditions that it's a mixed integer problem, you will allow for solutions that there's, for example, a half CH3 group. Or something. So it should, the result will not be usually a molecule that makes a lot of sense, but it gives me a target value. That's the best hypothetical molecule that can be described in this case with PC-SAFT. And I personally find this information really important because it tells me your process will not be better with any molecule that can be even fitted with PC-SAFT, and that's a lot. Your process will never be better than this or that performance. So it gives you an upper bound on your performance. Okay. And then we have this target value, and then we usually use standard optimization algorithms. In particular, auto approximation turned out to be very efficient for this formulation. So we solve the mixed integer nonlinear problem. We get a top molecule. But to be quite honest, usually it's more interesting to get a ranking of different candidates because a top molecule might, for example, not be commercially available. So what do? We introduce integer cuts, basically saying, please don't give me the same solution again. And then we solve the problem for the second best molecule and so forth. We solve this repeatedly. And if you want to look for this method, we published it under a long name. We call it one-stage CompCant, or because we do this relaxing step first, we call this continuous molecular targeting computer-aided molecular design. So we applied this method to the organic Rankine cycle I've been showing to you. And this is the very boring results table, which does not look exciting. But what information do we get? So I said, we get first a target information. This is the lower upper bound on performance, or here the lower bound on cost. Basically, our model says you will not be able to spend less specific investment costs. That's what the SIC stands for. Then about 3,000 euros per kilowatt hour. You will not find a better molecule in this. We can compute how much power, what's the output power, and this is the investment cost in there. So this is the target, and then we can look like for the groups we have, and I have to say for the transport properties, the groups are still limited, so that's why the molecules are not that crazy, but it's also molecules that have been discussed in literature, and we see like the real life, the real molecules are about 10% more expensive than the real molecules coming in, like propene or propane. They seem to be the closest ones in performance. In order to validate our methods, we compared ourselves to studies from the literature. So people have been collecting data from the literature on the prices of organic Rankine cycles, and you can define something like a Pareto frontier. And what you find is that basically our cost correlations and models really also lead us to models performance that is very similar in performance as what you find in the literature. And this also holds over the range of a greater range where we believe our model is valid. And I don't want to go into more detail, but in particular, it's also like the different cost contributions are correct. So that we are super happy. So with this, you have the toolbox I've been promising you in the beginning. So we are having these toolboxes where basically you can do the whole process, design process optimization, as you always know, but now underneath, I can really change the molecules that we are having in there. What's the next step? I call this here, let's go beyond simple cycles. What do I mean by this? Now, before I have fixed the flow sheet of my power plant, but that's another degree of freedom we could optimize. As for those who have been taking classes or courses or worked on power cycles, you know for sure that this is not the only option for a power cycle. This is actually the most simplest one. So we can make it more complex, and I changed it here to make it more complex. I added a couple of units. Let me walk you through this. So we had a simple ORC cycle, but what you can do regeneration. That basically means after the turbine, I have a recuperator that is a heat exchanger so that I cool down my effluent from the turbine and use it to preheat my fluid coming in. I can do something similar with turbine bleeding. That's basically I take out a side stream from the turbine, and we can also have an intermediate reheater. That is basically we have a two-stage expansion process, and I added an additional heater in the beginning. So we can add these units, and what is obvious, they all will increase efficiency, but my top molecule and top process and top flow sheet will balance the economics trade-offs. So we added more degrees of freedom. In particular, you needed 3 binaries, whether you go for these options, and then you can solve the optimization problem again. And this becomes nasty to do. And that's why we were super happy that we didn't have to write the model ourselves. But as you might gather from the screenshot, this is actually a screenshot from a flow sheeting software. In particular, this is a screenshot from GPROMs. And basically what we were able to do, or Johannes Schilling in particular was able to do, he expanded GPROMs basically, such as you could do GPROMs process optimization, and he added this new unit, which called CAMPD, obviously, of molecular design. So within a GPROMs flow sheet, you can now do the molecular design. And yeah, this has been published, and we have been doing so. And what you find, just for an example, if we go for the economic optimization, yeah, again, asking for minimizing specific investment costs, you will find out, an optimal working fluid again, in this case, 3-methyl-1-butene. And we'd say, okay, let's lose a recuperator, but no other options. Instead, if we run this on the thermodynamic optimum, you will end up with what you would assume. Basically, we do everything. We do this reheating step, we do the turbine bleeding, and we do the recuperator. So it really makes sense. It's really important to go for the economic optimization if you are able to do, because you end up with a different fluid and a different process. And again, this has been done now implemented in a prototype implementation. And I don't know whether Rafik is happy that I'm talking about other software. But this, unfortunately, this is only available to us in a prototype application. But
you are very welcome to do that.
Yeah, okay. And I have no financial interest, I should disclose. But I was very happy that we had this. I'm very unhappy that this is not part of a release yet. So feel free to bug GPROMs or I invite Rafik that we collaborate to enhance that this will become feasible, available to everybody. Okay. So this concludes basically the first part of my presentation, and just to relax you, the longer part. So what I wanted to introduce to you is the methods we have developed, and I want to make you aware that there's tools out there for the simultaneous optimization of molecules, process, and equipment based on powerful equations of state. And this development is continuing. But we're also complementing it because, to be quite honest, PC-SAFT is very powerful, but you cannot do everything well. So we're also employing methods from quantum chemistry to complement this. So basically, we have two pathways of doing molecular design. And in particular, I want to give a different spin to the second half of the presentation. I've been emphasizing money, but obviously money is not everything. We know, at least with the recent disasters, floodings in Germany we have seen, heat waves in the US, storms and so forth, that maybe optimizing the world only for money is not a good idea. We should care about sustainability and environmental impact. So what we wanted to do also with our methods is to extend them to also look at environmental dimensions during design. And for this, we need to expand again the model capabilities that we do have. It's no longer good enough to only look at the molecules and the processes, but what we really need to do is to look at the life cycle of the things we are using, at the products and processes we are developing and molecules, and to look at their environmental impacts. And as before, so this is an important topic, and I don't know how familiar you are with this, but I think many people have heard of it. So the idea is that we do a full life cycle assessment. That means I look at the things I create, the product, processes, from the whole life cycle. That is, where did I get my raw materials from? How were they produced? Was there transport and so forth involved? Then how do I use them? That's what we cared about before. Can I recycle them? And what's about the end of life? So the whole life cycle I have to look at, plus then I also should look at the different environmental impacts. And in this presentation, I will only look at global warming, but we should be aware there's more than global warming. And the challenge is that all I talked to you before in the last half hour was only the use phase of a molecule. For the working fluid, we have been looking at, I just looked at what's the economics of using it. I didn't look how difficult was it to produce it, how do I displace it in the end? And you might know, like from refrigerants, if you're old enough, we killed the ozone layer in the past because of basically power cycles of refrigerants we have been using. So they were excellent in the use phase, but they almost destroyed the planet in the disposal phase. That's why in order to do proper molecular design, you really should look at the full life cycle. And we do this actually building on another tool, on a second theme of molecular descriptors we have been using. And these are based on quantum chemistry and based on the so-called COSMO-RS model. What's the COSMO-RS model? Very briefly, this is a quantum chemistry-based model. And basically what you do, it's again a thermodynamic model, and the input the model needs is just the structure of the molecule we are studying. And then what you're doing a so-called Cosmo calculation, which is a quantum chemistry calculation, a so-called DFT, density functional theory calculation. And for this, we compute the surface charges of this molecule. Now, I don't know how familiar you are with this, but this can be, depending on the size of the molecule, these can be demanding calculations, quantum chemistry. Yeah, it's getting faster and better every day, but still this can be minutes or hours, and usually it's with interesting molecules, it's usually more than hours. But the power of this COSMOS method is that you need to do this only once for each pure component. Yeah? That is basically, I have one molecule, what did I have, propane or propene, that somebody had to do a DFT calculation only once. And then I can store the information in a database. And what's the information I need to store? It's basically a histogram of the surface charges. So what do? I take the surface, I split it into regions, and then I plot the like a probability density distribution of the surface charges. This we call the sigma profile of the surface charges. And here's the different molecules, how the surface charges are distributed over the surface. And this sigma profile is stored in a database. And then I do thermodynamic calculations. And these are standard calculations, basically the same like uniquark. So you do uniquark on these sigma profiles ultimately. And as you know, this is super fast. And then I do mixture calculations. So this is very, very fast. The good thing is this is fully predictive. So I can even do this for molecules that I don't need to train a group contribution methods. I will not go into detail. There are some fitted parameters in the COSMOS model people are debating, but in essence, if you use it nowadays, you can really come up with a molecule, you can dream up a molecule, and then you can calculate, do the Cosmo calculation, and then you can do very quickly prediction of mixture behavior. And we also applied this model, like standard as you buy, to a case study. And now I'm more on the chemical engineering side. And in particular, we, for example, looked at the production of formic acid. Why is formic acid interesting? Now, it's the most simple equation you can use for CO2 utilization. Because if you combine CO2 with hydrogen, the molecule you are generating is actually formic acid. So this would be, and formic acid is a chemical we are using and producing today. It's about 1 million tons globally. And my favorite use for formic acid, if you want to think what do you use it for, if you're into beehives and caring about bees, people put formic acid in beehives to prevent parasites entering the bees. So, and this looks like the most simplest reaction to take place with CO2. The only problem is it only looks so simple as long as you don't know anything about thermodynamics, because unfortunately the delta G of reaction is plus 41 kilojoule per mole in the gas phase. Or in other words, the equilibrium point constant is something like 5.5 to 10 to the power of 10 to the minus 6, telling you, yes, you write this down, but if hydrogen meets CO2, they basically never react to formic acid. Now that's a challenge to the chemists. That's why all the chemists in the world publish in all the good journals a new catalyst, something that still makes this happen, and then you get a nice paper published. But if you look into detail, actually most of these cases, they do not produce formic acid anymore. But what they do, they stick something to formic acid, basically to shift the equilibrium to the formic acid side. They form formic acid salts. Then I can shift the delta G, that's nice. But then I need a lot of energy to break the salt again. But then there was a beautiful paper coming out a while ago from the Lorenzi group. They found out, no, if I do this synthesis without salts or amines, that's what people have been using. If I do this in the right solvent, in particular DMSO, then I can increase the yield and I still do the direct conversion of hydrogen and CO2 to formic acid. And we were excited by this route and said, okay, people have not studied this experimentally, the whole process. Let's use COSMOS to predict the behavior of this molecule. And that's what Christian Jens did. And actually, I don't know, I'm not sure whether you're seeing him. And what he predicted, what Cosmo S predicted, is that formic acid and our new beautiful solvents, they form an azeotrope. Yeah, this is the vapor liquid phase envelope. And so the prediction was there was an azeotrope. I'm a huge fan of Cosmo S, but still you rather check in the lab. And that's what Bastian Liebergesell did in our group. And unfortunately, or fortunately, depends how you see it, Cosmo S was correct. There is a maximum volume azeotrope in there. So what you found is, yes, the Nature Communication paper was correct. DMSO is a beautiful solvent to shift the equilibrium, but you will not get formic acid out because it leads to an azeotrope. And if you do the whole process design, you will find out that it actually turns out to be less efficient than these formic acid salt routes. So then we came back to our toolbox, asking ourselves, okay, can we find a better solvent? And what I showed you, we do have a model, another model with Cosmo S to do prediction of here equilibrium properties. Now we need this link. Now we need to link this to molecular design. And here we are using a kind of group contribution method. In particular, we're using a genetic algorithm, which is called fragment-based, but it's actually the same idea. I have fragments or groups, and I'm using these in an evolutionary algorithm that I can combine different groups. I can have mutation, that is, I change a part, or I can cross over between different molecules, and then I come up with a new generation of structures being proposed. This looks like a group contribution method, but, and that's the important difference, with the group, with a fragment-based approach, I generate a structure, but this is a 3D structure of the molecule, and this 3D structure I then put into my quantum chemistry calculation. That is, then I do the full quantum chemistry. Yeah? And what is, for example, this thing can distinguish isomers and so forth, where some group, first-order group contribution methods have difficulties. I don't have any empirical description. I do the full quantum chemistry on this. And again, if the molecule is known from my database, I just pull it out of the database, and only for new molecules, I need to put them out there. Okay, so I do have a way to design new molecules and to calculate the properties. Then we need to do process design. And for the process design, I showed you we need to do this. And what most people probably have in mind, you should use rigorous models, for example, using Aspen Plus flow sheeting. And that's great because I get probably the most accurate result on this flow sheeting level. You can employ a different flow sheeting model, but these are the things to do. But they are usually very hard to converge. And in particular, I have to tell you, during molecular design, because I change the molecules insides, they turn out to be very difficult to converge. That's why many people go back to this, what I called initially the heuristic approach. I just optimize things like a partition coefficient or the equilibrium, direction equilibrium. But this is difficult to do because then I end up with a problem like we had before. Yeah, I do get the best solvent for the reaction, but it might suck for the separation. So how do I balance this? So they are very fast, but a strong simplification. And what we employ in our framework are so-called pinch-based process models that employ the full thermodynamic information, but they are very robust and efficient. And what's a nice thing, they have been developed in the group of my PhD supervisor, Wolfgang Wagwart. And I will just spend a very brief slide on them. What are these models? They are pinch-based. Basically, what we assume infinite long columns. We find a so-called pinch where the driving force vanishes. And we just have to calculate basically then 3 stages of a column, and we get information like the minimum energy demand, the minimum solvents demands, and so forth. And the good thing is about these models, they are very robust and they converge very efficiently, and their computational efficiencies, that is, we can employ them in a genetic optimization algorithm. So we employ the shortcut process models for reactions and separations. And then we can optimize them and look for different solvents like the ones we had for producing formic acid. Here's how such an algorithm then look like, our method, which we call Cosmo CAMPD. So we pick a library, say, okay, we want to consider these molecular fragments. then this genetic algorithm called LIA3D generates molecules. We do the property prediction using COSMO-AS. Then we do the process optimization, and that's basically the fitness value, the objective function value that Lea gets back. And then we optimize a new generation, and we cycle this till this thing converges. And so we applied this methodology I've been showing you to the formic acid synthesis, asking ourselves, I showed you CO2 plus hydrogen in DMSO is beautiful, but sucks in the distillation. Can we find another solvent that is good in the reaction, but does not lead to an azeotrope? Or we ask ourselves, okay, let's end up with DMSO, but can we break the azeotrope efficiently using an entrainer? Or can we, in a sense, put the entrainer directly into the reactor, that is, add a co-solvent to the reaction that does not too much harm here and help us in the output, that we can still distill off the formic acid directly. So we employed the machinery I've been showing to you, and these are some of the results. So what do you see here? That's the exergy demand, the energy demand for my process for heat and for electricity, because you can kind of trade these two offs. But what we want to be in the bottom corner. We want to have low energy demands. And the different points now indicate different solvents in different optimized processes. And the ones out here with high energy demands, they are alternatives to DMSO. And I have to admit, we didn't find anything useful close to DMSO's performance. This is the best entrainer, which was pretty good. And the other points, and in particular this gray triangle, that's a co-solvent. That is, we add something to DMSO that does not harm too much in the reaction, but that breaks the azeotrope. What's exciting about the triangle is experimental data measured by Martin Scott in the Leitner group in Aachen. And they did the measurements on DMSO, which had the highest yield, was also predicted by COSMO-S, only off by a factor of 2, but still the trends were correctly. And in particular was correctly predicted if you add acetic acid in the right ratio, you would halve the yield, but you could break the azeotrope. And that's what we also showed experimentally. So this toolbox led us really, and this is an industrial benchmark, to the most efficient route. Unfortunately, it turns out that DMSO and formic acid are not stable, but still I wanted to highlight that this toolbox really allowed us to very efficiently identify an efficient process. So this was published, and this same framework I've been showing you based on COSMO-S, we have now been expanding to do really life cycle assessment, as I've been pointing out. And basically all I showed you before was the use phase. So what do we need? We need to, for a new molecule we designed, we need to predict the life cycle impact of its production. And what we know quite well, and for this we have rigorous models for the end of life. But the first part, we needed models. What is the environmental impact of producing a molecule that only exists in the computer? And for this, we relied on data-driven modeling. Here we employed neural networks that use molecular descriptors to predict environmental impacts. And within our framework, we had to ask ourselves, what do we know about our molecules? And basically what do we know is the things we have been using in thermodynamics, in particular the sigma profiles and the other information from COSMO-S. And so what we did is we trained a neural network based on these molecular descriptors from thermodynamics. And here are some results. How does this work for the global warming impact, for example, comparison between a database value and the prediction. And what do you see? Yes, we capture the trends quite well. I also have to say it's far from being perfect. That's also why, because there's very few data and the data is of not always perfect quality, but still it turns out in our design, it's not most often very important to capture the right trends only. That's why we still need to work on this. We now have a model, the neural network model, that allows us to do the cradle to gate prediction for the production of molecules. And we can do the rest from our process modeling I've been showing to you, and also rigorous models for the end of life. Does this matter? Very often in engineering, we say energy efficiency is good enough, and that is already also very often true. In order to convince you that it's not always true, I plot here the greenhouse gas emission in a separation example over the energy demand. And since energy here is generated by burning natural gas, is the more energy you use, the more natural gas you burn, okay. But if I look again at the optimal process with the optimal solvent design, these are the results that you get. And you see, obviously, we can get close to the minimal impact of the energy demand, but then ultimately it differs. In particular, I want to point out that this production here, this is a logarithmic scale, so you can have a solvent that has the same energy demand, but still the global warming impacts differ by more than an order of magnitude. That is, there are trade-offs between energy efficiency and greenhouse gas emissions, and we need to look at the full life cycle in order to do so. And these tools are not yet perfect, but we are constantly developing them further, and they are already helpful today. So with this, I want to conclude, to give you the chance also to that we can discuss a little bit. So I wanted to emphasize that, like the SAFT, and it's not only PC-SAFT, it's a whole family of models that are available, but they are really powerful today. Also with quantum mechanics, I've not been pointing out, you can even do much more. We've been working on reactions and even catalyst design with this, because they have strong predictive power today. The toolbox of computer-aided molecular and process design is very efficient, and we can expand it from techno-economics to sustainability. So with this, I thank you for your attention, and I'm happy to take any questions.
Thank you, Andre. A very exciting lecture, a lot of new results. You have been very busy, I can see.
I'm trying to.
So there is one question here, actually several. So the first question is from Alejandro Pedroso.
Okay.
Is it possible to integrate an organic Rankine cycle in a plant to supply cooling utilities near at 0 degrees using the condenser at the end of the turbine?
Yes. Yeah, you can do sub-atmospheric cooling, if you have a demand for this. Yeah, this can be done. Would lead then to other conditions. Yeah, so the most case is basically then you have two plants. You have basically a combined, not heat and power, but cooling and power plant. We have not studies on this, but we have studies on combined heating and power. Yeah. Another exciting thing, maybe people are using organic Rankine cycle, are considering them for energy storage, to combine it with a heat pump. Yeah, if I have electricity, I pump up heat to a higher temperature level, then I store not in a battery, but a heat, and then I expand in the organic Rankine cycle again. And we also studied this, and can you can have like different working fluids and so forth. Yeah, but yeah, there's more opportunities in there.
Okay. There is another question from Dr. Wang. Molecular dynamics simulations. Would molecular dynamics simulation be useful in bringing PC-SAFT and quantum chemistry calculations? Bringing together, I mean.
Yeah, actually, in a sense, yes. In the design context, I have to admit, but maybe Rafik, you can comment. I didn't find molecular dynamics simulations actually very useful to do in the optimization context, because they're very heavy. Yeah, and actually, so we have not employing this directly. It's useful to get more insights and more information to study systems in detail. But if you put it into an optimization framework, then this becomes a real bottleneck. So what actually I'm aware we have been using, our collaborator Joachim Groß has been using it the other way around, actually. For example, to fit molecular force fields, he has been using PC-SAFT because you can really link them theoretically directly, like develop a mapping between these parameters. And then you can basically do the optimization in PC-SAFT and then extract the parameters of the force field out again. So we have been more like avoiding the molecular simulations as part of the optimization, but it's something that complements the systems, and you could use it, for example, in afterwards. Yeah, if I would rather do the optimization on the coarse-grained level, you could call it PC-SAFT. And then, for example, to do the transport properties, I then do a molecular simulation studies to learn about this in more detail. That at least has been our approach.
Yeah, it's one thing that we did was that we use molecular simulations or dynamic simulations in the case of polymers and gas permeability through polymers. There we use molecular simulations to generate, let's say, pseudo-experimental data. And then we use that experimental data to make a group contribution model so that in future we didn't need that.
Yeah, yeah.
But even that one to generate, let's say, pseudo-experimental data for two polymer, polypropylene and polyethylene, for a reasonable number of carbon numbers and temperature pressure, it took 3 years of a PhD student.
Yeah. Okay. So I feel supported by you, and I have to say, maybe I think I was misreading the question on the cooling utilities. So you want to so basically what you need you need basically the Rankine cycle takes up heat on the high temperature level. So you would need even lower heat to do the cooling. So I was confused. Yeah. I think I misread this. So the organic Rankine cycle by itself, no, you can use it only to generate power, and I need to reject heat at the lower temperature level. Yeah. So sorry, I have to. I was reading the question now. I misunderstood. So, but you can apply the same philosophy to heat pumps to produce cooling power. Yeah, and then there's a lot of gambling at the moment in heat pumps to integrate them into systems, and that's very exciting. But the organic Rankine cycle needs a high temperature heat source or higher temperature heat source and rejects at the cooler side. Yeah, yeah. Sorry about the confusion. Yeah. Okay, there's
a question, a raised hand. Please let Lucas ask his question.
Yeah. Thank you very much for the nice presentation. You showed that we can use neural networks to predict the environmental impact of molecules. But I think in the cycle for the life cycle, so not just use phase, also other things, you mentioned that we can also use neural networks to predict other environmental impacts. Did I understood that wrong, or which other impacts can we predict with things like machine learning?
So what we did is we trained always, what we looked at specific is cradle to gate. That's basically what are the emissions from producing a chemical till we buy it. Yeah, that part, because that was unknown to us. And we did only, that's data you also find in commercial life cycle assessment databases. And that's what we use as training data. And we did not only do global warming impact, but basically there's methods. We had like 18 different environmental impacts: ozone depletion, toxicity, and so forth. And the methodology worked actually in the same way for all of these impacts. But I think there's still work to be done. In general, it works, but the problem is, and I think you can improve it probably from the machine learning side. But at the moment, to me, this is really data limited, because we have very little data on life cycle assessments. So if you look into like the largest chemical database, EcoInvent, if you look, they have not very many chemicals, organic chemicals in there. We're talking on the order of 200 or something. So you have 200 training points to train a neural network model on something. And actually, if you look into more detail, most of these points are not good data, because they are not industrial data. They have been estimated based on very simple models that you can write down in 2 lines. Yeah, and so if you cut this down, you are down to 80 molecules that you have for training, and that is a real issue to me at this point. But still, my example, I said, even though the error bars were large, it kind of pointed us into the right direction. And we did an error propagation. And for the optimal molecules, because we kind of avoided the very bad ones, there the uncertainty did not matter that much anymore. But I think it's, yeah, we're working on the data side, but I would also be happy to look more into machine learning models to apply better models at that point. Yeah.
Okay. There was a question on chat and also a raised hand by Christian Waring. Are you able to read the chat also?
Yeah, I have it now. Okay, I read the question to everybody. What is your comment on carbon capturing machine in Iceland, taking into account its energy cost? Yeah, I have done a study on this. Yeah, thank you for picking up my comment for the discussion. Yeah, so the comment I made yesterday, there was the opening of the largest direct air capture plant. It's now able to capture 4,000 tons per year of CO2 from the air. And then what you do it, and that's special in Iceland, they put it into a geological formation where it basically forms very rapidly, surprisingly rapidly, stones, basic carbonates are formed. And you can even go online, and I'm still financially not attached, and you can buy CO2 certificates from them. And I have to say, it's still quite expensive. And that's maybe the first half answer to the question. As a private person, at the moment, you would pay 1,100 euros, or no, it's Swiss francs, but it's 1,000 euros then per ton of CO2. So it's 3 zeros. So it's still super expensive, and that relates also to the energy costs. So we did a life cycle assessment on this technology, and what you can say is that it's really reducing the CO2, and actually to do this in Iceland, where the power is very clean, is a good idea. So basically, from every CO2 that you capture and you put it into stone, basically almost 950 grams are really the negative emissions. That's great. Yeah. We also did on the energy demand, and the energy demand is large. That's why you need clean electricity. If you use the German grid, the current grid, for example, you would generate more CO2 by generating the energy than you are saving. And also overall, maybe to make this clear, because some people believe we will save the world by direct air capture, this will not be the case. We would need more energy than we are producing today, electricity, to capture all the CO2 from the electricity. Yeah, so this is not the silver bullet to save the climate. Yeah, we have to forget about everything useful on energy savings, on renewables. It's really something we need in addition. Yeah, that's a bad thing. If you look at IPCC models, they are saying it's not good enough to go to net zero. We need to go to net negative. Yeah, and that's what this technology is about. But it's intrinsically energy expensive to capture CO2 from air. Yeah, very true. I hope that was helpful. And Christian?
Okay, there's a raised hand by Christian Waring.
Yeah, hi, Andre. Thanks for the great talk. One
Thank
question
you.
Concerning the ongoings of CAMPD developments. Could you discuss briefly something regarding dynamic design? Because we saw steady state calculations from Johannes. Yeah. So is there any progress like Dominic did, or you're planning to do this?
No, yeah, thank you for the question. Yeah, you're very right. In this application, I only showed steady state applications. But in principle, you can design, you can also design dynamic problems. This becomes numerically more uglier because I have a mixed integer dynamic optimization problem. Yeah, so we are fighting with this, but it can be done. And we have been, for example, looking into the optimization of an organic Rankine cycle to put him on a truck, yeah, where the exhaust gas is fluctuating in time. And we can then take this into account in the design and also in the selection of the working fluid. So this is doable, but it's heavy. So what we are also doing is at the same time characterizing when do I need to do this and when can I avoid doing this. So basically working on characteristic time constants to say, yeah, when can I avoid doing this? But it's in principle like being an academic and having time till my retirement. It's easily done, yeah, but it's still not, at least for the tools we have in hand, it's not something that it's computationally heavy, yeah.
Okay, there
Yeah,
seems to
thanks.
be one more question we can take maybe. It's on chat. You can read it.
Okay, that's from Juan, and he asked, what descriptors did you use for the neural network model? How do they link to the LCA impact you are predicting? Yeah, the selection of the descriptors is obviously very important. What we used here is actually, and that was a nice thing, we only used the information we were already using in the molecular design. That is, we had basically the SMILES code of the structure, the molecular structure, and we had the sigma profile. And with this, you could get already the same quality as other people have been showing in the past. And this has also been confirmed. There has been another paper where people use the same Cosmo-S information using group contribution methods, so linear models. And they also saw the same quality. Yeah, so it's far from being perfect, as you have seen, but at least you can already capture trends based on this. We extended this. The more information you put in about the process, the better you get, obviously. But even just descriptors of the molecule we are producing, that's the only information we put in there.
Okay, so thank you very much for a very exciting presentation. I hope you will continue in this direction and maybe give us more new ideas and results in future.
No, thank you again, Rafik, for inviting me. Thank you all for listening. And yeah, I'm glad that you got the community together and gave me the opportunity to spread the ideas and also to spread your great work. Thank you very much.
You're welcome. So before we start our last session, where Orakoch and Siripon will show some problem solutions with our software. It will not be the detailed simulations that Andre was talking about. It's more the molecular design part, but we do have process verification also. But I just want to also remind everybody that on the 16th of September, we have the last of the webinar series for this year, which will be on modeling. And Professor Jay Lee from Korea, KAIST, and Professor Fenji Yu from Cornell University will join me in giving guest lectures on fast and reliable computer-aided modeling. And that will include data analytics, machine learning, surrogate modeling, all those things, plus mechanistic model, which I like. So all of this will be on the 16th of September. So now I will let Orakoch and Siripon show their problem solutions.
Okay, thank you.